Oh, hello. Thank you very much for persuading me to do this. If you had a physicist, you've had a chemist, you've now got the lowest form of mathematical knowledge of them all, which is the engineer. So I apologise now. There is no maths in this at all, but it is an appeal for those that are great at theories to maybe help me to understand these mysterious liquid crystal things better, so that I can make useful devices and we can go on and make hugely successful companies out of it, etc. So there's a strong commercial edge here, there's a strong industrial connection through what I do in the research. And somebody mentioned, it might have been Peter Collins said, mathematicians are always trying to find a unifying theory for things. Well, if you can find a unifying theory for optics and liquid crystals, please, I'm your man. I'll be the first person to buy your software or whatever. Because one of the problems I have is that there's many, many pieces to the jigsaw puzzle, and always trying to put them all together is a real headache. So my title is my first title was Flexo-electricity doesn't really exist. That was deemed to be a little bit too controversial, so it's slightly different now, and I'm quite glad now because there's quite a heavy flexo bias in the room with Rachel and Cliff and Peter and various other people, so yeah. I'm actually quite glad I'm not saying anything too controversial. However, it's one of these interesting electro-optic effects. As an engineer, I see it, I watch the helix go, and I go, oh, hey, I want one of those. And then I try and make a device, and it doesn't quite deliver what I expect it to deliver. And there are lots of unknown things I don't really understand about it from an engineering perspective. So I'm going to try and give you an engineer's view, which at times will be rather vague and rather diffuse. But what I'm trying to do is trying to pick up some theories and some concepts as to how I can actually put together these devices and make basically a phase modulator. A phase modulator is a very useful item. There are lots of people who are interested in this, and there's just a few which we work with, from the big boys of BAE Systems Kinetic, as was, and one of their left, probably not anymore, and Alps Electric, a big Japanese components manufacturer, small startups like Light Blue Optics and Holoxica, and probably the most successful company at the moment that's doing anything with phase modulation is Finisar, and they are an Australian company who use holography in optical telecoms to do optical fibre switching systems. And there's a huge interest in holography because it's a very efficient way of moving light around, whether it be displays or telecommunications or other applications. There's also more wacky things like correlation and adaptive optics, which are out there as well. And it promises an awful lot, but it often falls down at the device level. And one of the big breakthroughs in the 90s, where Bill was a huge pioneer, was liquid crystal over silicon technology, combining silicon VLSI circuitry with the lovely goo of liquid crystal to make very tiny miniature displays that allowed things like projection, etc., to go forward. And has been a big technological step forward. However, there's also some limitations from that, and that comes back to this issue of the material inside the device and how it interacts with the light and how it delivers the sort of thing that we want for particularly holographic type applications. So I'm going to sort of lump telecoms, optical holographic projection, 3D displays, they all come under the same hat when it comes down to the device that you're trying to implement in these systems. Blank slide, not good. What's going on here? So what is a hologram? Just first of all, don't think of these fancy 3D pictures that you see on the back of postcards, etc. A hologram is basically a computer-generated pattern in our case, and that computer-generated pattern generates another pattern, which might seem a bit pointless. However, this relationship between these two patterns is quite elegant. It's basically optical diffraction, as predicted by Huygens and then Fresnel and Young. And the relationship between the two is quite simple, lovely mathematical transformation, the Fourier transform. So it's a very powerful and simple way of moving light from one plane to another in a very sophisticated fashion. And what we do in holography is we calculate these random patterns or these special patterns in such a way that we want to generate a particular image or a particular replay field or a general pattern of some sort. And so we end up with an array of apertures, which is essentially like young slits but scaled up enormously. All those slits interfere with each other and give us our desired replay field. We then change the hologram, we get a different replay field. So we've got a mechanism which allows us to control two planes independently via this rather elegant process of diffraction. And that's what we do in holography. Problem is, we want to generate a hologram, we have to be able to display this information in a useful fashion. And I have here a nice binary hologram, one of my very first when I was a PhD student many years ago. And it's binary, it's black and white, therefore all the black bits are blocking light. Therefore it's not a great way of moving light from one plane to another because half the light in that image is being lost in absorption. So what we do is we take away the polarizers and we just use the phase of the light. If I just represent those apertures purely as phase, i.e. a +1 and a -1 state in its most simplest form, I get exactly the same replay field, but now I get all of the light in the replay field, a bit of the light in the outer orders because there's various associated repetitions from the Fourier process, but I get majority of the light in that central order, which means I can then very accurately control where the light goes in my replay field. So it's a very powerful mechanism for moving light in optical systems. This is why telecoms love it. They put fibers here. You can then change this pattern by changing the hologram, and you can send light from one fiber to another. And that's what Finisar do in their optical switch systems. The problem is the technology that allows me to do that has some limitations. And we really want to be able to ramp this up, particularly for things like holographic projection, 3D displays. We want more pixels, smaller pixels, and we really want fast pixels. We want apertures that can modulate the light very, very quickly indeed. So here's my noddy reason for why phase is important. Basically, I can use interference through the process of diffraction. This is as complicated as my maths gets, by the way. So I can get constructive and destructive interference, and therefore I can use all the light where I want to use it, and I don't lose anything in the actual modulation process. I only lose light in the diffraction process. And it's also robust to defects in the device, etc. I won't go into that, but there's lots of other advantages. But yeah, it's a very nice and efficient way of moving light from one place to another. And here's some examples of some real commercial products out there. This is the fourth dimension display ferroelectric on silicon liquid crystal device. There's a hollow eye pneumatic on silicon device, and this is the light blue optics holographic projectors. This image is not generated by image projection, it's generated by diffraction. There's a hologram, like that funny black and white pattern displayed on a ferroelectric liquid crystal device, and what we end up here is a nice colour image, red, green, blue laser, etc., into this nice picture. And one of the big problems they have is, as you can see, it's all a bit in a darkened room. Why isn't it a darkened room? Because it ain't quite bright enough. It's only 15 lumens, and they want to have more like 30 lumens, and they really can't get any brighter because about 2/3 of the light is being thrown away inside the projector purely because of the binary phase. It's a binary +1, -1 phase modulation device in there. It's also not perfect. It's more like +half, -1/2 really. And what it's doing is it's losing that light in the diffraction process. It's all being essentially dumped inside the box. So what we get here is a relatively inefficient image. However, it's going really fast. This is actually 2,000 frames per second you're looking at here. You're looking at an average, which is why you're getting a nice clean image, noise reduction, etc., because it's using noise reduction and frame averaging to remove the noise in the image through a series of sequential holograms, each with independently generated noise. So there's a very clever algorithm design that's gone into generating this image, but it's not bright enough. And that's a limitation of the modulation scheme. This is just me standing in front of a holographic projector. This is the British aerospace application. This is a head-up display. This is the sort of symbology that you see on a head-up display. And the reason why British aerospace like holography is because if a pixel dies on the display, that death of that pixel is spread by the Fourier transform all across the background of the image. And so you don't see any degradation in the image until about 20 or 30% of the pixels are dead. And then you start to see essentially an increase in the zero order and a decrease in the brightness. But it takes a lot of destruction in the device before you start to see serious damage in the actual image. And that's important because this number here might be the height above the ground, which in a plane is quite important. And you don't want to have an 8 become a 5, and suddenly before you know it, you have landed too quickly. So that's why they like this. It's a very popular. It's also very bright and does green very nice, as you can see, which they like as well. So the perfect phase modulator allows us to essentially control the phase of the light through a system. And a great example is the old school Gaborian holographic film holograms, where essentially you have pixels that are so small, buried inside a photographic film, that you get really quite complex phase modulation. You get depth modulation as well. So you get quite a complicated modulation function. They're very, very small pixels, very, very large number, very high density. However, they are fixed. They're holographically recorded within the actual material itself. Therefore, I can record one hologram and then I have to get another piece of film, record another hologram. It's not a very dynamic or very quick technique, also quite pricey. The other holy grail is embossed or etched relief surfaces. This is the perfect phase modulator. So I take something like incident plane wave. I have some sort of stuff. This stuff is essentially anything that's essentially transparent, and it has some sort of profile associated with it. And I have a refractive index difference between the air and the stuff. And what happens quite simply is, of course, light travels through the material and it goes through a thicker part of stuff here. than it does here. So when it comes out the other side, this bit's got through ahead of this bit, and the difference between the waves is the phase. And that is our perfect phase modulation. What I want is a liquid crystal effect that does that. And I don't know of one, and if anyone does know of one, please do tell me. There's lots that sort of potentially might do it, but they're always limitation of this, whatever. They're never quite there. Most importantly, this stuff is isotropic. It could be glass, it could be plastic. It doesn't have to have birefringence. Therefore, this can be independent of the polarization. I don't want polarization modulation, and what I always get out of liquid crystals is nearly always some sort of polarization modulation. And one of the problems I have as a non-mathematical engineer is that I have great difficulty telling polarization from phase. Sometimes they're quite interlinked and quite subtly related to each other. This is where the unifying theory of holography would be very useful, because it would allow me to relate this model of what a phase modulator should do to what things like a pneumatic or a ferroelectric or a flexo-electric or a distorted helix or some other wonderful electro-optic effect actually does to the light, both in terms of its actual phase retardation in this sort of model versus what the electric field's doing and the polarization, etc. So that's kind of my holy grail for my holographic application. So I want phi to effectively be independent of polarization. Problem is, this is still fixed. It's stamped out of a piece of plastic. It might be on your Christmas cracker wrapping paper and look very beautiful and pretty from the diffractive effect, but it is still a permanently recorded phase profile. What I want for my projectors and my switches is a reconfigurable way of doing this, and that's what I'm sort of trying to achieve in terms of the research. Leading into the commercial interest, this is really what we need from our device in terms of delivering a viable holographic system. So the problem is, we really want a fast multi-level phase modulation. We want reconfigurable. We don't want to have to emboss it, stamp it, record it photographically. So ideally we want electronic, although this could be optical. There's a whole range of devices that are optically addressed, like photorefractives, etc. Optically addressed devices, optically addressed liquid crystals, Janussi effect, all sorts of wonderful things which could be optically, but ideally we really want to be able to turn electronic information into optical information. I want more than 2 pi phase depth. I want to be able to retard the wave by more than 1 wavelength. That's very important for many applications, and really the thing that's a problem at the moment is that I want to do this within a millisecond. In fact, I'd like to do it within a microsecond, but within a millisecond would be awesome. Within 100 microseconds would be amazing, and probably a lot of money would be made indeed if we could do this kind of modulation effect. And this is why I go back to Flexos, because Flexos dangle tantalizingly in front of me like the Holy Grail, thinking, I'm just like, can't quite get it. It offers all this, you get this, but you don't get this, or you get this, but you don't get this. It's like, it's like juggling sort of, bags of jelly. It's really, really frustrating. For the solution, we've already seen ferroelectrics in the LBO device. It's fast, but it's binary, therefore I'm always throwing away light there. Pneumatics, they're multi-level, they're grayscale after all from displays. They can give us a variable refractive index, which is fantastic, usually with an out-of-plane effect or a twisted effect sometimes, but they're slow, they're goop, they slosh around, they're very, very slow, and getting sort of down to a millisecond response time is still the holy grail for the mainstream display industry, let alone the holographic industry. Trying to get fast electro-optics is also very important for things like active backlight devices, etc., in the displays market. So breaking that millisecond boundary is very important for 2D and 3D flat panel normal displays, not just holographic systems as well. So this is still something that's holding back the industrial approach to these systems. So I'm going to talk about Flexos now because Rachel's done all that for me, so I don't need to discuss it. But this is the Maya version, the fantastic shape anisotropy, and this is the dreaded Bouligand cut. We know who Bouligand is today from the BLCS talk from John Lydon. We said that if we have this twisted helical structure and we lie the helix in the plane, then we can essentially get the sort of distortion that we need to mimic that same shape anisotropy that we've seen for the funny shaped molecules, and therefore we can get electro-optic effect which starts to resemble something useful in terms of a phase modulator. So the simplest model, and Steve has asked me to apologise because the helix in this is not quite the right way around, but don't look at it too carefully. Rachel's picture was much nicer. But basically, I have this helical structure, and I can distort the orientation of this helical structure by applying electric field either side of it. And if I can get it lie down in the plane, and I can put polarizers around it, then I can start to modulate the light for an intensity display. And if I get the amount of angle tilt of this axis correct, then I can also start to modulate the phase of the light in the system. So this is starting to look like a very useful and very interesting electro-optic effect because it's fast. It has microsecond response times. Therefore, I'm very attracted to this. However, it is a very frustrating electro-optic effect because there are so many things that just don't quite work properly with it. Things like alignment, things like trying to control the materials, etc. And trying to get a big enough tilt, which is another big problem for the phase modulation aspect of it. We want to have a very large tilt angle, therefore we don't have to have polarizers in our system, and we can get that holy grail of polarization and sensitive phase. So this is simple materials that have been done many years ago. So you can see tilt angles up to sort of 40 degrees, vaguely linear, which is the proof of Flexo-electricity, I'm told, and more importantly, response times down below the magic 1 millisecond. Therefore, this has so much potential, yet I still cannot make an LCOS device that has this material in it that works reliably. And why, I don't know. I need to know this information from the clever physics, chemistry, and mathematical people out there who can tell me what is it I'm doing. Is it ions? I don't know. It could be anything that's going on in these materials. I don't understand the physics of it at all. There's a very simplistic model that I have. I have a wave plate. I rotate that wave plate through an angle. I do a Jones matrix. I get myself a number. I'm happy. I make a device. I make the device, I test the device, actually Rachel tested the device, and we get completely different numbers. And so it's very difficult to add up what we think the optics are doing versus what the engineer's version of what it is. We don't really understand what's driving it. There's lots of nice theories out there, but often they're buried in complexity of the physics and the mathematics. And what an engineer really needs is kind of an end translation of that, which gives me a number like birefringence as a function of voltage or something where there's something really simplistic that I can plug into a nice elegant optical model, and then I can build useful devices with it. Because that's probably, I only need a few parameters. I need thickness of the device, delta, and I don't need much more than that to make a useful phase modulator. However, those numbers turn out to be very difficult to actually obtain in a meaningful way, particularly birefringence. I mean, finding out what the birefringence of a flexo material is really quite a difficult question, it turns out. There are lots of averages and bits, that and the other, but I've never really come up with a convincing answer. Most people say, well, go and measure it, and then you measure it and you get something which doesn't quite match what you think it should be, but there's still some interesting problems out there which we're trying to figure out for these particular structures. So there's a few questions I'm trying to answer at the moment. Like Rachel, how do I orientate this epoxy helix? How do I get it to lie down and behave itself in or out of plane? And actually, Flynn did some work a few years ago where you can essentially, rather than having the helix in the plane, you have the helix sitting out the plane, so you have the Grandjean texture, and you can tip it this way and that also optically looks quite exciting as an electro-optic effect because you've still got a variable birefringence, and that could be as harnessable as a in-plane ULH type structure. However, I still need to know how to analyze it and how to make a real device out of it. Is it really phase or polarization? That's a question that's bugged me for years, and no amount of Jones matrices can help me because I still don't really understand exactly how I can get a perfect phase modulator out of this in-plane rotating helical structure. What is the actual birefringence that we see? How does it vary with electric field? All these things, and how then do I essentially relate that to a bimesogen or a particular electropneumatic and a cholesteric chiral dopant and a given device geometry? How do I come up with a recipe so that I can go to Hamamatsu and say, here I want to make your sub-millisecond LCOS device. Here's the various parameters you need to make your device. Here's a bottle of goo. Go away and do it. How do I do that? Well, at the moment I can't because there's no easy recipe for alignment, for materials, for exactly what the electro-optic effect is going to do. And that's one of the problems that we're really trying to unravel. And then there's this. The most famous picture of them all, the one display ever made with blue phase in it. I'm sure there's only one. There's only one picture anyway. If you type blue phase display, that picture turns up about 50 times. It's a Samsung and their polymer stabilized blue phase display. It's a lovely electro-optic effect because it has an awful lot of interesting symmetries associated. There's some of Flynn's pictures I don't understand at all, but what I see is an average director profile, an average refractive index, which really the wavelength of the light scale looks like essentially a perfectly variable birefringent material, which is what I want for a phase modulator. I want to be able to change the refractive index or change the birefringence with an applied field, but these are even more mysterious Because, okay, we now start to understand how we make them and how we can control them and maybe even make rubber out of them, but we still don't know really how to put them in a device and apply a field and get a variable birefringence or a phase modulation out of the system. So this is a more advanced topic for phase modulation, but once again, it has the potential of being very fast, and if you look at the way in which the molecules line up in these twisted structures, you also get the option of having polarization-free phase modulation. You can essentially take the direction of the molecules out of it and make essentially it a perfect phase modulator, but we're still trying to figure out the best way of doing this. And it particularly gets difficult when you start to distort this structure of an electric field. You start to unwind it or you start to bend it in various ways, then the whole thing essentially becomes really quite complicated, quite chaotic, and it's very difficult to predict the optics. So I can get some degree of tunability, but I can't get the perfect 0 to 2 pi or 0 to 3 pi phase modulation that I want for my holographic applications. So once again, my shopping list. I want to understand phase versus polarization modulation. Is a very simple, fundamental question, but actually quite elusive when you start looking at in-plane versus out-of-plane, electro-optic effects, twisted helixes, distorted structures, etc. Is multi-level phase at speed really possible, or is it something that's just never going to happen? I mean, I find it frustrating even in ferroelectrics. You go back to the old-fashioned ferroelectrics, symmetric C, you get essentially a nice 22-degree tilt material that responds in, say, 10 microseconds, like DRA2, those of us remember the vintage days of these materials. Fantastic material. However, you up the tilt angle to some other 45 degree, which is what I want for a perfect phase modulator, and its speed plummets. It goes from 10 microseconds to 10 milliseconds, and I'm back to being no better than a pneumatic. So, you know, these sort of higher tilt materials also tend to be rather slow. So there's kind of this inverse relationship between the speed of the material and its tilt angle. So how do I get that into a useful device that makes me a phase modulator? I don't know. So maybe highly twisted effects are the answer. Maybe even DHF, which seems to have fallen off the radar a bit, although I've got this background theory that DHF and flexo-electrics are the same thing. Those of you that know what distorted helix materials are, they were very popular when I was a PhD student, and they had offer that same in-plane tilting helical structure that we see now with the flexo materials, and it was fast, but they were also a nightmare to align as well. And we need to essentially unify this process. For an engineer, I need to know, basically I need a recipe book. I need Delia's Book of Optics. I need to know, I want 3 biomesogens, I want 2 5CBs, I want to mix them together, I want to put them in a cell that's 10 microns thick with a plain and iron alignment, bake them in the oven for 3 hours, and I've got myself a phase modulator. Then I can go off and make my holographic displays happen. So that's kind of what I'm trying to do with these systems. That's kind of the problems that we're trying to solve with an engineering hat on. I apologise, there's no Maxwell or Grandjean or Ericsson, Scene, Frank, whatever thing is in there. I can't remember the names. So, how many time?
You had about 22, 3 minutes.
Okay, I'll stop there. There are some other issues I would like to address as well, like for instance, when you get into the theory of holography, to make really good holograms, particularly 3D holograms, you want to have very, very small pixels. And one of the questions I don't understand at all with crystals is how small a pixel can I make? How much can I constrain that refractive index within a space? Because for a good hologram, I want to be submicron. I want to be 200 or 300 nanometers type periodicity structures, which I can control, not just twist and wind up, or I want to have essentially multi-level control of the molecular structure at that kind of length scale. Is that possible? Is that realistic? Or is that a pipe dream of a mad engineer? Because if I can, then I can essentially make the perfect 3D displays. I'll skip out 3D. But for instance, Kinetic, who showed us we could do this several years ago with this beautiful full-color 3D holographic system, but they used actually an amplitude hologram, and they used a very large box that you can't quite see behind this. It has a very expensive, very high-resolution display, and it basically a tiled-up series of little crystal displays which create sort of 10 to the 8, 10 to the 9 pixels, which then create a massive bank of young slits, which allows you to create really quite superb interference. And if you've seen this thing, the pictures don't do it justice. It looks really good. I mean, it's really fantastically, shows how good a 3D image can be if it's done properly with a holographic system. So you can replicate all the rays that you would see from the original object. None of that autostereoscopic two-view malarkey. Good old-fashioned, what the actual eye would see from the real object, which is what you get from a pure hologram anyway. However, the cost in this particular system is that it's very complex, has quite a lot of optics and a very, very high resolution display. So they've used essentially pixel density to make this kind of quality image. I'm hoping that we don't have to go to the sort of 10 to the 9, 10 to the 10 pixel level. We can do it with more modest resolutions, but use more complex phase, more complex modulation scheme. This is a ferroelectric based system effectively, so it had a binary modulator in it. So going to multi-level would give us a little more flexibility and maybe not require those massive pixel densities. So the problem with this particular structure is that we're now limited to our parallel plate design capacitor pixel. We're using a display device to do effectively a holographic job, and we don't really particularly want square pixels. We don't want to have well-defined little areas that are essentially limited in their physical area. We want a more dynamic, we want a more cuneiform type structure like you'd see in a perfect photographic film hologram, where you have a continuously varying refractive index profile at the sub-micron wavelength scale. We need to be able to do this dynamically with an electric field applied. So we need something like a liquid crystal within these structures to create really good high quality 3D holograms. So if we're trying to mimic the perfect 3D hologram, which is the photographic hologram, and there's some people using polymers in places like Arizona at the moment that are using photo-addressed polymer systems to recreate sub-micron resolutions in polymeric materials. So I'll just skip this, but basically one of the things we can do is we can use nanotechnology to try and bring the length scale down to the order of what we want to be for holography. So this is an example of an array of carbon nanotubes growing on a piece of silicon. These are periodicity of 0.5 micron, and they're like conducting wires. And so what I can do with that is I could use the conducting wires to essentially create a microlens, and that microlens is then constrained by the periodicity of the structure. So here I've got 0.5 micron, and here I've got some 1 micron pitch lenslets, which you couldn't make that very easily without using something like a nanotube to confine the electric field. Basically, you are smacking the liquid crystal so hard that it has no option but to go where you tell it to, because it is absolutely distorting it to the point. And this is a mistake device. This should be 3, 5, and 7 micron pitch lenses, but the lithography went squiffy and they all overlapped each other, so I ended up with some 1 micron pitch micro lenses. But I can turn them on and off with this electric field, so I can reconfigure liquid crystals at these length scales. The question now is, can I do it in a more controlled fashion? This is essentially a uniform array where I switch everything either on or off. What I want to be able to do is individually address those little nanotubes and therefore create this perfect version of a photographic hologram. And liquid crystals are still the most promising material for doing that, but I don't understand at all the physics of the materials at these sort of length scales, as to how we manipulate them, how they operate. People tend to work with display pixels, which 100 microns if it's a TFT, maybe 10 microns if it's an LCOS device, but nothing at the 1 micron pitch scale. So there's not much out there that really has that sort of ability to do it. There's one device, I think, from Colorado, which is a blazed grating system that had sub-micron pixel elements, but it didn't use the same kind of field enhancement we get from the nanotubes to really hit the liquid crystal hard and make it do what we want. So there's some inkling of potential there, but trying to unravel this is really a whole mathematical playing field in its own right, because I haven't got a clue how these devices function. We can do at the moment is we can do essentially this kind of modeling here. This is a COMSOL electrostatic model, finite element mesh model of the system. But then beyond that, we have to essentially superimpose the liquid crystal profile using a very, very noddy refractive index model to try and work out why we get this kind of lens structure from that particular electric field profile. I know the nice chaps at UCL have had a go at trying to figure this one out, and it doesn't. There's lots of variables like surface anchoring and how the interaction between the nanotube and the liquid crystal is exactly like. I mean, why do you get these little black dots that you can see quite clearly at the tips of the tubes when they're only 50 nanometers in diameter, so they shouldn't be optically resolvable, but yet they appear quite clearly in the pictures. What is going on at the tip of each individual tube, we don't know, and that's with them switched off as well. That's no field applied. So there's some sort of distortion of the liquid crystal just purely because of the tip of the tube. Trying to figure that out and then switch it is still one of our key objectives in these sort of systems. So that was my rant about phase. That's part one.
Yeah, do you want to take some questions now?
I'll take some questions now. Part two is is kind of related, and it's Bill's bit, so I can't do it anywhere in much detail as Bill could. But I have a vague idea of what he's going to say. Anyone else?
I was going to ask about, you said that the analogue response from some of the high cone angle ferroelectric crystals was much too slow, even though it gave you the analogue response. Well, you could still, in the Ford application, the car application that Kinetic was doing, the speed wasn't critical at all.
Yeah.
But you could still do the analogue modulation even if it was 1 millisecond. And my second point was DRA2 was a mixture deliberately targeting 12 microsecond response
I know,
times.
it was wonderful.
And no one ever said, well, let's do DRA3, which doesn't have the symmetric A phase, gives you the wide cone angle, but will give you, admittedly, it will be slower inherently, but it needn't be milliseconds. And
Well, there was the dreaded CDR8 that I believe alerts
oh, no, you
in
don't want that.
the murkiness of history somewhere.
But it's just,
We won't go there though.
it's just, there's a small, very small project to get you an analogue response
Yeah.
from an FLC with a much higher phase modulation
Yeah.
than you've got today, and it just hasn't been done.
Well,
And it would be easy to do.
I agree. On the ferro side, we've got a lot of materials that are 22 degrees because that was what
Yeah.
was developed for
Was
display
required.
applications.
Yeah.
But only 2 or 3 that are beyond 22. So that the Slot-Zane CDRR materials are one example, and there's the Chisso materials which have a 44 degree tilt. But they're like much slower. And I don't know if there's an inherent relationship between the speed you can switch them versus the
It goes with science great things,
Yeah.
but it's
Yeah.
not that big. It's not 2 orders of magnitude. It's
I don't know. It's like I say, but it's not my. It's something I need some help
Next
with.
question is, on the carbon nanotube array, is it a plan, or have you thought about actually putting those on top of a photoconductor to make an optically addressed spatial light modulator, and then you can get benefit of your 5 micropixels? Presumably that's your
Yeah.
next step to do that.
Yeah, although based on what we did on optically addressed devices many years ago, back in the darkness of time, getting sort of below 5 microns with a lot of photoconductors was quite difficult. Whereas I can grow these things at 500 nanometers,
Oh,
so
I see. Yeah.
I need to be. But I want something. What we're trying to put circuitry underneath. Because, with the CMOS device, I can go down to whatever it's 100 nanometers resolution. I don't need much field to switch these things, so I don't need many volts. What I want to be able to do is have individually addressed nanotubes. However, the problem with that is that the growth process happens at 700 degrees Celsius, and there ain't many silicon chips out there that can survive 700 degrees Celsius. So what you do is you grow a tube on a melted pile of mush, which is not terribly helpful. We are trying, but the problem is doing anything on a silicon backplane is expensive. Not something you can just wash up in the lab. It's where you need to have your TSMCs or your Samsungs to do the chip design and the fabrication. So it's very difficult to actually manufacture those devices.
I've got 3 people here. I think Tim's hand
Right,
is up
yes.
first.
The Samsung device
Yes,
with the pretty blue face and stuff.
the nice lady. Yes.
Yeah, the nice lady. And you said we don't understand. I mean, is that a comment that, we are running behind these Koreans and they do understand? Or is that a comment that...
My personal opinion is that because there's only one photograph of this device, suggests it might be quite hard to make.
So you think they don't understand?
I've never seen 2 in the same room.
I've seen 2 in the same room.
That was at SID probably.
You have to go to the right room.
It's a very big room with a lot of wallets in it.
I've
Yeah.
got 2 at home too.
Oh, okay, cool.
There's a rather bigger one as well.
Yeah, excellent. They should put a picture on the web and I could use it. I'm sick of that lady's picture. It's not even advertisement. I mean, blue phasers have a lot of really exciting potential, but it's just, to me, they're a complete mystery. I mean, Flexo is a kind of a sort of a slight mystery, or slight smoke and mirrors. But I'm looking at a black piece of glass for Flexo. I don't understand at all for blue phasers exactly how I can use them as a device structure. But they look tantalizing, like they do the right things. They have this, ideal refractive index property that I can use to make a phase modulator. But I don't know how to harness it. I don't know whether it's going to give me the grayscale I need to do it. But hopefully, now that they're much easier to make in the lab than they have been in the past, we can actually start to build devices and test these things out.
There's lots of other Hewlett structures and liquid crystals, of course.
Yeah, I'll take anything. God, once it's the light We've tried the various cholesteric things. Problem with these, a lot of these materials is that they have these weird third states, these scattering states, photonics they suddenly ping into for no reason. Phil taught this morning on lenses. One of the companies we're working with is plagued by this photonic state. Just randomly, their device will suddenly scatter, and then it'll be fine again. So you get this lens where suddenly for about half a millisecond it flickers into the scattering state, and that's really quite annoying if you see it happen to you. And we don't have a clue why it does this. We're trying desperately to control the field and all the parameters so that the thing will stay in the state we want it to be, but every now and then it just goes ping. And is it the device? Is it the ITO? We don't know what it is, but it's very, very frustrating.
I think we're running a bit late. And
Okay,
Tim said
my second part is much shorter. So.
Well, yeah, I don't.
No, it is, 'cause I
believe you.
That's why I wrote the slides during Chris talk. So.
One more. That's
It might be preempting what you're about to say for the next talk, actually, but I think there's some very interesting issues to do with the fact that you've got these very high resolution electrodes that you could put in potentially with LCOS, and you've got all this complicated phase and polarisation and so on. And you've got the fact that you want to calculate the Fourier transform, and you know how that's constraining your calculation of the Fourier transform. But I think there's probably some extremely interesting issues to do with how you calculate the patterns that you want, given that you've only got a certain range of values. But that may be.
If you go back to this device here, if you're going to put a field on these individual structures, you get a Gaussian profile, which becomes like a mode. Becomes like a fixed structure you can sort of vary with the electric field. When you put two together with different fields, that mode changes. You get really quite a complex structure of electric field, and that becomes like the things that Phil was talking about with the lenses, how you actually control the refractive index with this field structure is a whole different way of thinking about pixels, because it's no longer just a parallel plate capacitor, it's now got a third dimension of depth which you can control. So yeah, it is quite part of the algorithm.
I don't know if I'm allowed to it's on this point.
I'll let you, don't worry. I can override him. I'm bigger than he is.
These are multi-wall nanotubes.
They are indeed,
They are
yes.
open on the top.
Yes.
And the liquid crystal go inside, which it should, I guess, given the size.
They're not hollow. They're called
They're
tubes,
not.
but they're concentric rings of
Yeah,
carbon.
they are multi-wall, but they
Yeah.
still have
They're actually onion skin. So there's not a lot of space inside them. But I mean, in theory, because the molecules are very small,
Yeah.
they should be interlinked with it. What the interaction is between the carbon and liquid crystals is still one of the questions that nobody understands.
I was wondering about the liquid crystal going inside the hollow part. I mean, just inside the nanotube.
It may do, but it's a very small hole.
I mean, there is evidence, isn't there, of the alkyl chains locking onto those sorts of graphite type structures.
There's lots of, but the whole relationship between...
So it may be, but it's really difficult to know what actually it's doing on the surface there, I suspect.
The top of that tube is the catalyst.
Yeah, it has a
which
blob of
grows
nickel
up.
on top, yeah.
So it's got a seal on the top.
But they're still hollow. They're like a sieve. They're hollow. So
So that is nickel or metallic?
it's a nickel lump on top. It's a ball. Yeah.
I thought it was going from the bottom.
No, the bottom growth. But you can get ones that have an open top, and you don't see any difference from the electro-optic. But the whole relationship between graphene and liquid crystal is really unknown at the moment, and trying to figure out how graphene and liquid crystal interact is one of the problems we're looking at the moment.
Graphene is fascinating.
That's why we're in there. We're on the bandwagon, don't worry. I take money from anybody, don't worry.
Okay,
Even
I think
graphene.
we'll take any more questions
Yep.
up in the final session if we need to. Just explain, just for those who didn't hear, that Bill Crosland, who should have been giving the next talk, is indisposed. He's got a leg problem and can't get out of his house. So Tim has very kindly agreed to stand in.
I'm going to try. I think I know what you're going to talk about, because he talked to me about it, but it was one of those Bill conversations where he